Hello everybody, getting ready to do lesson 10.1 part 1 of pre-calculus math today, the classwork lesson. And for today's classwork lesson, you will have 12 points that will go into your notebook, and 40 points will go into your classwork sheet, name, date, period, and then due date here for my homeschoolers and onliners. And teachers will start out, students, with they'll work for today. Solve the quadratic equation by completing the square here. This is v squared plus 3y. I think this is 3. No, I guess no, it's be 3v. I'm sorry, it would be 3v. So it'd be v squared plus 3v minus 2 equals 0. Okay, so do that one. And do this one. You give your students about 5-6 minutes, teachers. Pause your video and see you for the solutions. Okay, welcome back everybody. For hopefully by now you're done. Up here, what do we do here? We take 1/2 of 3, then square it and add it to both sides and move our 2 over to the other side. So now we got a perfect square here. V plus 3 over 2 quantity squared equals 17 over 4. And then down here, and then, well, wait a minute. V plus 3 over 2, we're going to take square root of both sides, plus or minus radical 17 over 2. And so V will equal the negative of 3 over 2, plus or minus radical 17 over 2. And then down here, we're going to take 1/2 of 7, square it, and add it to both sides. Move our 19 over. Take the square root of both sides now, and then what do we have then? So this becomes z minus 7 over 2 equals plus or minus 5 times radical 5 over 2. Then we move our 7/2 over, and then we have z equals 7 over 2 plus or minus 5 over 2 multiplied by radical 5. Into today's lesson, the three-dimensional coordinate system. Recall that the Cartesian plane is determined by two perpendicular numbers called the x number lines. Two perpendicular number lines called the x-axis and the y-axis. These axes, together with their point of intersection, the origin, allow you to develop a two-dimensional coordinate system for identifying points in a plane. To identify a point in space, you must introduce a third dimension to the model. The geometry of this three-dimensional model is called solid analytic geometry. You can construct a three-dimensional coordinate system by using a z-axis perpendicular to both the x and y-axes at the origin. So here is our z-axis here, x, and then y. Then you have your different planes down here. So the positive portion of each coordinate axis, taken as pairs, the axes determine three coordinate planes, the xy plane, the xz plane, and the yz plane. These three coordinate planes, like this, yz, xy, xz, these three coordinate planes separate the three-dimensional coordinate system into 8 octants. The first octant is the one in which all three coordinates are positive. In this three-dimensional system, a point P in space is determined by an ordered triple x, y, z, where x, y, and z are as follows. X equals directed distance from yz plane to P. Y is the directed distance from the xz plane to P. And then the z equals directed distance from the xy plane to P. Okay, that's good. So a three-dimensional coordinate system can have either a left-handed or a right-handed orientation. In this text, you will work exclusively with a right-handed systems. As illustrated, it's called a right-handed kind of orientation where you revolve in a counterclockwise manner like that. In a right-handed system, octants 2, 3, and 4 are found by rotating counterclockwise 2, 3, and 4. 2, 3, and 4 around the positive z-axis. So this would be 2, 3, and then 4 would be here. Octant 5 is below octant 1. Octant 5 is below octant 1. And octants 6, 7, and 8 are then found by rotating counterclockwise around the negative z-axis. So these are found, octants 6, 7, and 8 are found by rotating counterclockwise around the negative z-axis. So that'd be down here. That would be below your xy plane. Okay, so knowing all that, we should be able to plot points in space, right? So to plot the point 2, -3, and 3, notice that x equals 2, y equals -3, and z equals 3. To help visualize the point, locate the point 2, -3 in the xy plane. So 2, wait a minute, where would it be? 2 would be here, then -3 would be out here. So this would be 2, and then -3 would be out here in the xy plane, denoted by a cross. So this would be 2, -3 out here. So it'll be out here. Then we go up 3 more. So then we have 2, -3, and then we go up 3. So that would be that one there. 2, -3, and then 3 would be this point right there. The point 2, -3, 3 lies 3 units above the cross. So they're calling this a cross here. Then you go up 3, and that'd be your point there. Because now we're tying into our z-axis here for that point. You can plot the others, so -2, 6, and 2. Let's see, -2, 6, so we go -2 under x, and then 6 under y, and then 2. That'd be up here, right? So that'd be our positive direction there. So that'd be our -2, 6, and 2 would be out here. 2, 6, 2, 6, -2, I'm sorry, -2, 6, and then 2 up like that. And then 1, 4, and 0. So our positive here would be 1, 4. Where am I at here? 1, 4, and then 0. So 1, 4, 0. So it'd be x would be 1, then 4 to be out here, right? 1, 4, and 0. How come they got that -1 here? This is the negative side. Okay, so it'll be positive out here. 1, 4, and then 0 will be right here. Yeah, this is the negative side of the x-axis. This will be the positive side here. So it'll be 1, 4, 0 would be this plot right there. All right. And then 2, 2, and then -3. So 2, see 2, then 2, then -3 would be a drop down there. So that would be this one here. 2, 2, then -3 would be down here. Okay, so that's how all that works. Okay, then let's try one. Plot both points in the same three-dimensional coordinate system. So we have a 3, -1, 0, then -4, 2, and 2. So for this one here, students, I'm going to let you do that one. For this one here, 3, -1, and then 0. So 3 would be out here. 3, -1, -1, and then 0. That'd be out there somewhere. So here we are here. So 3, -1, 0 would be right there. And then -4, 2, positive 2, and then up 2 would be up here. So that's how we arrive at that word. So the distance and midpoint formulas, okay, what's that? Many of the formulas established for the two-dimensional coordinate system can be extended to 3 dimensions. For example, to find the distance between 2 points in space, you can use the Pythagorean theorem twice as shown. So we can use Pythagorean theorems on finding distance. Like between those 2 triangles, you can use Pythagorean. The distance formula in space, the distance between the points x1, y1, and z1, x2, y2, and z2 given by the distance formula in space is, so we get this big long radical here, x2 minus x1 squared, y2 minus y1 squared, z2 minus z1 squared, and then we add these together, and then we take the square root of them. Okay, well that sounds cool. Finding the distance between 2 points in space, find the distance between these 2 points. So here is our distance formula in space, and then we're going to plug in our values from up here, 1, 0, 4, 1, -2, -3, and then we do our combining like terms. So we have 1 plus 9 plus 25, so we have the radical 35 would be our distance there between these 2 points, and that would be how you would do it. So let's try one now. Find the distance between the points. So we have a point here, and then we have a point here. So 7, 4, 8, and then 3, 2, -5. So of course we're going to use the formula up here, 7 minus 3, 4 minus 2, 8 minus the -5, 8 minus the -5, and then we combine, and then we square, and then we take the square root of 189, reduces down to 3 times radical 21 is what that comes down to. So that would be an example here of how to do that. Notice the similarity between the distance formulas in the plane and in space. The midpoint formulas in the plane and in space are also similar. So the midpoint formula in space, the midpoint of a line segment joining points x1, y1, z1, x2, y2, z2, given by the midpoint formula in space is, here it is right here, x1 plus x2 over 2, y1 plus y2 over 2, then z1 plus z2 over 2. So that sounds about right. So now we're going to try one here between 5, -2, and 3, and 0, 4, and 4. So using the midpoint formula in space, the midpoint is, here we go. So we're going to combine these two, and then these two. And then we're going to divide them by 2, and we end up with 5 over 2, 1, and then 7 over 2. Would be what we would come up with using that formula. And then this would be the diagram of that here. This would be the visual, this would be the analytical, then this would be the visual. I'd much better have the visual up and then go from the visual. But sometimes you can't do that, so you do it this way. Okay, so let's try one. Find the midpoint of the line segment joining these points here. Here's our 2 points. So how will we do that? Well, okay, so we have these 3 different parameters here for plotting, and we come up with our 3 points here. We combine our values here. -6 and 4, 3 and -3, 10 and 4. We divide those by 2. We ended up with 0, -1, and 7 as our plot. So here is, see, what would that be? See, 3, -6, and 10. And then -3, 4, and 4. And then here's your line between the 2. And then this point here, 0, -1, 7 would be about here. So that'd be the way that it would look in a visual manner here to finding your midpoint of this line here. This would be the analytical, this would be the visual. That would be in there somewhere. So that is 10.1, Part 1, Pre-Calculus Math classwork. Here's my email, animatedpowerpointmathvideo@aol.com. Thank you very much.